So measure of location tells you where the data is, where the distribution is. Measure of variability describes the shape of the distribution. Okay, so there are five: range, interquartile range, variance, standard deviation, and coefficient of variation. We'll start with the simplest one, range. Okay, so range is a very quick way of understanding the data set. Gives you a visual idea, right? And it's very simple. You just simply take the largest value minus the smallest value. Okay, so we're going to use the above data, use this data set, and let's find the range. So first find the max, right, which equals 715. Find the minimum, which equals 525. Okay, so the range simply equals 715 minus 525, right? And this gives you, right, the min and the max. Okay, and so this tells you that the overall range here, oh, let me finish the calculation, 190. Okay, so this tells you the range of the data set or the population is 190. Okay, next, interquartile range. All right, so interquartile range, right, represents the middle 50%. So the range represents all the data. Interquartile range represents the middle 50%, and we're going to be using Q3 and Q1. So clearly, you have to find Q3 and Q1 first. Okay, we found those earlier. Let's go ahead and copy it down. Q1 is 545. Q3 is 625. Okay, so the IQR, the interquartile range, is 625 minus 545. Okay, which equals 80. All right, visually, here is Q1, Q3. Okay, then that means 80. So that means 50% of the data in the middle has a range of 80. Okay. Right. Now, a quick note. Right? Why do we need both of these? One, the range is sensitive to extreme numbers. So if your distribution has some really small numbers or really large numbers, right, then it's likely to pull the range apart. Okay, IQR, right? Because we're only looking at the middle 50%, right? So it's not sensitive to that. You can have extreme numbers on either end. It's ignoring that. Okay, and if again the idea is if I want to get a better representation of the overall population, right, the IQR might be a better choice. Like usually, most of the time, depending on what the purpose is. Now, it's important to keep in mind that both of these, the range and the IQR, only uses 2 data points. Okay, so when you want to start thinking about the idea of efficiency, right? Should I ignore all of the other data? Right? Should I only use 2 data points? All right, now variance and standard deviation is the most important of all the measure of variability. It is the most commonly used, right? And as I hope you see why. Right? So it utilizes the more important aspect of variance, right, is that it utilizes every observation in the data set. Okay, so conceptually, it represents the average deviation of each observation, right, or each data point from the mean. Okay, so let's go through the motivation here a bit. Okay? Suppose, right, I want to develop a measure. Right, I want to find the average distance of each data point, right, from the mean. Okay, I want to see how far, right, is let's say if it's income, right, then if it's income, right? So for example, here let's do it up here, right? For example, if the average income is 80,000, right? If the average income is 80,000, right, and that is X bar, right? Then if you make 120,000, right, then your distance from the average, right, it is 40,000. Okay. Now, if you make $60,000, okay, then your distance from the average is 20,000. Okay, and now yes, it is minus 20, but let's say I don't care about that, right? Let's say that all I care about is how is the income distributed, right? And I hope you can see how that might be useful, right? A population with a very small deviation, right, then we will consider that more equal. A population with a small deviation, that means most people makes around the average. Right? A population with a very large deviation, that means you have a lot of people that are very poor and you have a lot of people that are very rich, right? So everybody's kind of spread out. Okay, so that might be good or bad, right? Depending on what you're measuring, right, and depending on, right, what you're trying to do. Okay, so this is a very important measure, and we want the average distance. We want the average distance here. Okay, so here's just a thought experiment, right? So suppose I want to create such a measure. Okay, so here is my average. Now I want to think about it in the population sense. So let me go ahead and write the mu here. Remember, mu is just average. Right? And then here is my observation x1. Okay, x2 might be over here, x3 might be here, x4, and so on. So I have all these distance from the mean. Okay, all right. And to get this distance here, right? This could be x4 minus mu, right? I could get that number, okay? X4 minus mu, right? And to get this distance here, this will be x2 minus mu, right? So I can do that pretty easily. I can just subtract the mean, right? And then get get the distance. Okay. Now, if I want to find the average of all the distance, well, I could simply add it up, right? I could add them all up and then divide. Okay. But here's the problem, right? x2 minus mu, right? Because x2 is smaller than mu, is going to be less than 0. x4 minus mu, okay, because x4 is greater than mu, the way I draw it here, is going to be greater than 0. Okay, what happens if I add a bunch of negative numbers and a bunch of positive numbers? Right? They're all going to cancel out. Right? They're all going to cancel out from each other. Okay, all right. So one of the ways we can get rid of that, well, one, we could do absolute value. Okay. However, it turns out that absolute value is very difficult to do math on. Right? It's not a very effective or efficient operator. So instead, we're going to do the second best thing. We're going to square it. Okay. So if we square it, let's say we take x2 minus mu, and then we square that, it's going to be bigger than 0. And if we take x4 minus mu, and we square that, that's going to be bigger than 0. Okay, it will always be bigger than 0. Whenever it will always be positive whenever we square anything. Okay, and then now we can just do that. We square it all, and then we add it all up, and then divide. All right, we divide, and so that is variance. Right, the variance, which we will call sigma square. Well, here, let me write this there. So variance, then as a definition, right? Variance as a definition, right, is summation, right, xi minus mu squared. I minus average, take every observation minus the average, square it, and then I divide it by n, the total population. This is by definition. That is variance. Okay. Now, however, by the way, because we're talking about in terms of population, we're going to introduce a Greek letter. So this is sigma. Sigma. All right. So sigma squared. Right, this is sigma squared. Okay. But remember, we want the average distance. We've squared everything now. So now all the units are messed up. So we need to unsquare it. We need to take the square root. So what we really want is sigma. So we take the square root of sigma squared, which is the variance. So which that means we take the square root of the summation of xi minus mu squared over n. All right, and that is the origin of sigma, which we will call standard deviation. Okay, all right. Now, that's the definition of standard deviation. Okay, and then I just told you this is the true story of how statisticians come up with the definition of the standard deviation. And the whole goal, right, is to find the average distance of each data point from the mean. Okay, now For the mean, right, we have sample mean and population mean, okay, and then and so now we have sample variance and population variance. The only tricky part here is our sample variance is going to have a different formula than the population variance. Okay, now the reason behind this, all right, we won't go into too deeply, and hopefully when you get into future higher level statistics class, you can understand this for yourself, right? But the reason for this is because our sample statistics is always going to be an estimate of the population statistics, or we call population parameter. Okay, and so but to make sure that the estimate is unbiased, right? To make sure the estimate is good, right? We need to adjust the formula a little bit. Okay, so we won't go deeper into why we need to minus one here, but that is necessary to make sure that our estimator is good. Okay, all right. So so then we can just calculate this, and the operation wise, right? And by the way, in practice, right? In practice, we'll always do this anyway, right? This is the sample variance. We'll always have the sample. We, in theory, in practice, we never have the true population anyway. So we always calculate this, right? So let's give this a try. Let's find the sample variance and the population variance for the following data set. Okay. You know what? Let's go ahead and just ignore the population variance part. We don't need that. Let's just go find the sample. Let's just find the sample variance. Now, to find the sample variance, first thing you need is to find x bar, because the formula is you need to find the average first, right here. Okay, so I went ahead and put that in the calculator. Just add it all up and divide it by 1, 2, 3, 4, 5, 6, 7. Let's just write n equals 7. Right, I add it all up and then divide it by 7. So I got x bar equals 38. Okay, so I did that on the side. Okay, once I did that, then I can set up my table. So we talked about this in the math review. The best way to do variance is to do the table method. Okay, the table method is xi. Okay, so first I'm going to copy down everything here, and then now this does not need to be in ascending order, so that's okay. And then I'm going to take xi minus x bar. Okay, and then I'm going to need my last column is going to be xi minus x bar all squared. Okay, so I'm going to go ahead and just copy it down here. 43, right? 35, 34, okay? 58, 30, 30, 36. Next, I'm going to take 43 minus 38, 35 minus 38. Okay, every number minus 38, and we'll fill in the column here. And then, after I'm done with that, I'm going to square it. Okay, so go ahead and pause the video and try yourself, and then check your answer when you're ready. Okay, that's my first column there. I just subtract 38. Next, I'm going to square everything. So this will be 25, 9, and so on. Go ahead and pause, try it. All right. Next step, I want to do summation xi minus x bar all squared. So that is this column. I'm simply going to add up everything here. All right. Once you add that up, you're going to get 582. Okay. All right. Now, to get the sample variance, right, I'm going to need 582, and I'm going to divide it by 7 minus 1, n minus 1, and that is going to give me 97. Okay, all right, and then to find the sample standard, to find the standard deviation, I'll just have to take the square root. All right, and actually, you know what? Let's go ahead and calculate the population variance. I don't know why I stop you there. And so let's go ahead and find sigma squared. Okay, and the only difference here between the two is the numerator will be the same. Okay, and the denominator, instead of dividing it by 7 minus 1, just divide it by 7. Okay, and then here I got 83.19 or 14. Okay, a quick word. Here, if we're calculating the population variance, right, the assumption is that this is the entire population. Okay, this is the entire population, and our mu, our population average, is 38. Okay, so this is again, this is a purely theoretical exercise, right? It will, we will never have a population this small. And if we do have a population that small, we wouldn't really care about it, right? So this is clearly something this small is clearly a sample, a subset, okay? But if right, we assume that this is the entire population, then this is the notation that we would use appropriately, okay? All right. So a couple notes. Unit. Okay, so the unit of the variance is a square of the variable. So if this is dollars, right, then when we square it, variance will be dollar squared. Okay. Now, of course, right, dollar square is not a thing, right? It doesn't mean that you have squared the money. It's just nonsense, right? So we need to take the square root, right, to bring it back down to make it a proper measure. Okay, and so that's what we call standard deviation. Okay, so let's use the here. I'm gonna recopy what we got earlier. So we got S square equals 97, sigma square equals 83.14. Okay, and that's fine. The sample standard deviation and the population standard deviation, very simple. It's all just calculator work. Take the square root of 97. For sigma, you would take the square root of 83.14. Right? Okay, and then simply pop that in your, calculator. Okay. So it is true that standard deviation, right, tells us, gives us a sense of how the population is distributed. Okay? However, we still need a measure of location, right, the center, to put it in perspective. Okay? For example, suppose you know the standard deviation for two different populations. Sigma A is 12, sigma B is 4. So population A, I have a standard deviation of 12. Population B has a standard deviation of 4. Which population has a more variability? Now, at first glance, right, you will just, you should say A. Okay. However, this really depends on what the mean is, what the population mean is, right? Because consider this, right? If this, let's say, was income data, right, and if you have a very large deviation, which is measured in dollars, for example, but if you have a very high average income, then the deviation might not matter. However, if you have a low deviation, right, but then the average is really low, right, then the deviation, right, relatively speaking, might have a more impact. Okay, so we call that coefficient of variation. Coefficient of variation allows us, right, to scale the standard deviation according to the mean, and then we can make a comparison. Okay, all right. So, and by the way, it is always expressed as a percentage, but the calculation is simple: standard deviation divided by the mean times by 100, and we can express that in a percentage. Okay, good thing for sample and the population, the calculation is exactly the same. Standard deviation divided by the mean times 100. Okay, so let's calculate the coefficient of variation for both of these. Okay. All right, we don't have a notation for them, so, but here we go. So this is simply 12 over 24 equals 0.5, so that gives us 50%. Okay, whereas here, right, population B is 4 divided by 6, which equals 0.67, which gives us 67%. Okay, this paints a much better picture. Relatively speaking, right, in population A, the standard deviation, right, only proportional is only 50% proportionally of the mean, whereas population B, it is 67%. So therefore, we will say population B is more variable. Or we can say it has more variability. Okay, and here we go. Here's a quick summary of the formulas that we have just gone over. All right, here's some more definitions. Okay, again here, just keep in mind this chapter is all about tools that we have or we're learning to describe a distribution. Okay, and so one of the things that we have already talked about is the idea of skewness. Okay, and that is a measure of the shape. Here's the formula. Don't worry about it. Don't freak out. You'll never have to calculate. Okay, but although it's not that bad, right? Skewness is, we know what these are, n over n minus 1, n minus 2, and then you have summation notation here. Okay, all right, but don't worry, you'll never have to calculate it, so ignore that. You can feel free to ignore it, but just know that it is there. All right, what's good about now? You will have to know, however, what happens when this number, okay, is positive, negative, or 0. Okay, so if you plug that in to your calculator or put it in a spreadsheet, and if it's positive, that means the distribution is skew right, such as this over here. Right, so this will have a skewness, a positive skew. Okay, and we can see it here. That's a 0.85. Okay, right. Tail is longer on the right. Mean is greater than the median. Okay, if it's negative, then it's skew left. So you can see here, right? Tail is longer on the left. If skewness is 0, then it's symmetric. Right? Okay, so now we have a numerical measure that tells us the shape of the distribution. Okay, and you can see here highly skewed. Right, so here's the highly skewed right, and now the skewness is 1.62. Okay, so I'll just give you a simple example. Again, you don't have to calculate this, but this data set that we've been working with, right? Yeah, it is a data set on monthly rent. It must have been pretty old, a monthly rent, right? If we plot this in the frequency distribution, right, a frequency distribution, and we can plot the histogram here, we can see the skewness, and we see the calculated skewness is 0.92, and indeed we see that there's a tail going. The tail is longer to the right. One last thing on measure of location. All right. Suppose you see a specific observation and you would like to know where is that relative to the mean. Okay. Right. For again, let's use the income example. Right. If you meet somebody who lives in a city that you're visiting, and that person tells you, right, their income is $35,000. Now, whether or not that is high or low, right, depending on what the average is, right, depending on how far, right, that observation is from the average. So a z-score is really just that. It is a measurement of how far an observation is, right, and by standard deviation. So for example, if an observation has a z-score of 3, that means it is 3 standard deviations above the mean, right? If a z-score is negative 1.1, then it is 1.1 standard deviations below the mean. Okay, all right. So where is this useful? Well, in the class, for example, right? So let's say that you have a student here, and they're taking math and history. Okay, and here are their grades. Or not their grade, excuse me. Here's his grade, right? In math, he's getting 72. History, he's getting 85. Okay, here's the class mean, and here's the class standard deviation. Okay, so in which class is he performing better relative to his classmates? Because these classes are graded on the curve, so this is the important part, right? Not the actual percentage. Okay, all right. So then to figure it all out, we just calculate z-score for both. Okay, now the z-score formula, you've seen this a couple times already, right? It is simply take the observation minus the mean divided by the standard deviation. Okay, for the sample and for the population, they're both the same. Okay. And we use subscript z math, okay, and z history. Okay, and this is going to equal 72% minus the mean 64. Okay, I don't need to put in the percentage because everything is in percentage already. Okay, 85 minus 75 divided by 6. Okay, go ahead and put it in the calculator. Okay, this is going to equal to 1.67. Okay, all right. So what does this tell us? What does it tell us in math? Right, he is 2, right, standard deviation above the mean, the class mean. Right, in history, Right? He is 1.67 standard deviation above. Okay? Therefore, he's doing better in math. Okay? Or is it doing better in math? All right. Let's look at one more example. Okay? Now, a person is considered a genius if they have an IQ that is 3.4 standard deviation above the mean. Okay, suppose the population mean, mu is 100, and the population standard deviation is 16. How high does one's IQ have to be considered a genius? Okay, all right. Let me give you a graphical representation. Okay, give you some intuition here. Okay, let's imagine that the IQ is normally distributed. In fact, it typically is. Okay, but let's say here is 100. So that is the mu, right? The average IQ is 100. Okay, so the IQ point that the IQ number that we're looking for is 1, 2, 3.4 standard deviations away. So that number. So we're looking for that number. Okay, and remember here, standard deviation is 16. Okay, all right. So the question is, what is that number? All right. Now, if the standard deviation is 3.4 standard deviation above, that means the z-score equals 3.4. Okay, so we're going to use this formula in reverse. Okay, to find out what x is. This is the IQ number, the IQ score that we need. You take 3.4 and you set it up like this: equals x minus 100 divided by 16. Okay, now the rest is just algebra. Multiply 16 on both sides. You get 50.4 goes x minus 100. Then finally you get x equals 154.4. Which means if your IQ is 154.4 or above, then you are considered a genius. And that's it for handout 3.2.